The numerical problems related to distribution factor and breadth factor and distribution factor KD. Let us solve some problems. Calculate the distribution factor for 36 slots, 4 pole, single layer, 3 phase winding. 36 slots are there. Poles are, number of poles are 4. Number of slots per pole for phase is 36 by 4, it is 9. Number of slots per pole for phase we can calculate as 9 by 8 is 3. 9 by 3 is 3, number of phases will be 3, hence it is M equal to 180 by, what is M? Number of slots per pole for phase. Number of slots per pole already we calculated, 9 by 3 gives 9, it is number of slots per pole for phase. Now slot angle beta equal to 180 by N, we will calculate 20 degrees. Distribution factor can be calculated as sin M beta by 2 by M sin beta by 2. That is equal to 0.96 is the distribution factor. It is always less than unity. Similarly, we can calculate distribution factor for different, if the 3-phase alternator has 120 slots, alternator has 8 poles, number of slots is 120, 3-phase, number of poles P is assumed as 8 poles, number of slots per pole for phase we have to calculate, that is equal to 5, number of slots per pole, that is pole pitch equal to 120 by 5, 120 by 8, that equal to 15. Now the KD sin M beta by M sin beta by 2, if you substitute, you will get 0.957. That is the numerical problem related to synchronous generator. Now we go for EMF equation of synchronous generator. That is very important, and how the EMF varies. If you know EMF equation, in case of DC generators, pi Zn P by 60A is the EMF equation. In case of AC generators, the same equation we can't apply. It depends on EMF equation of synchronous generator alternator. It is depends on pitch factor, form factor, all this will be, and the number of poles, number of flux, total number of flux lines passing through per unit area. Assume that so many terms we have to assume for to derive EMF equation. Flux per pole we assume that phi. In DC machines also we assumed as a phi, whereas phi P equal number of poles, Ns is synchronous speed, and F is frequency of induced EMF, and Z is total number of conductors. Z per phase is, for Z or number of conductors, 3 phases are there. Z phase is calculated by Z by 3 is gives 3. If number of phases equal to 3, if you substitute conductors per phase, how many conductors, total number of conductors is assumed that 120. For each phase, how many conductors? 120 by 3 gives 40 conductors comes under one phase. KD is distribution factor that can be calculated by using formula M sin beta by 2, sin M beta by 2 by M sin beta by 2. Pitch factor, coil span factor is given by cos alpha by 2. Form factor is RMS value by average value, that is RMS value, substitute RMS for an average value, so you will get sinusoidal EMF. What is the RMS pitch factor? Form factor is 1.11. The form factor of RMS sinusoidal waveform is 1.11, is the ratio of RMS to average value. Consider a single conductor placed in one slot. The average induced EMF in the conductor is d phi by dt. Conductor. Okay. If you consider one conductor, when conductor moved with respect to flux, d phi by dt. For one revolution, the rotor average EMF per conductor is flux cut in one revolution by time taken for one revolution. For one revolution, the total flux cut in one revolution is pi into p. The total flux cut in one revolution is pi into p. Time taken for one revolution is 60 by ns, because we consider synchronous speed. Ns is 120 F by P, 60 by ns. Then EMF induced, E average per conductor. Average EMF induced per conductor is pi p total flux divided by time taken for one revolution. If you divide pi p by 60 by ns, pi p ns by 60, make it as equation 1. But ns equal to 120 F by P, if you substitute here, you will get, by substituting ns equal to 120 F by P in equation, average EMF per conductor is pi p by 160, 120 F by P. If you, then average EMF per conductor is 2 pi f volts. Average EMF induced per conductor is 2 pi f volts. If there are Z conductors, we have to multiply Z. One conductor, it is Z number of conductors may be multiplied, Z is multiplied with that, it is Z pi f into 2 pi f into Z. We multiplied, then it is average EMF per phase. Assume full pitch winding for simplicity, but we are using short pitch windings. The conductors are connected to a one conductor is 180 degrees electrical apart. Hence, resultant EMF per turn will be twice of EMF induced in conductor. Because 2 ES already. 2 ES we assume. 2 into EMF induced is 2 pi f 4 pi f volts. Let T phase is the total number of turns per phase connected in series. Assume concentrator winding. All conductors are placed in one slot per pole per phase. Hence, EMF per phase is algebraic sum of EMFs per turn. Average EMF equal to E phase equal to T phase into average EMF. Therefore, average EMF E phase equal to T phase into 4 pi f. Turns per phase into 4 pi f. Therefore, E phase equal to 4 pi f T phase. RMS value of E phase, if you multiply RMS value for that, 4.44 pi f, if you multiply this 1.11, that is form factor for this RMS value of E phase is this one. This is the average value. What is our form factor? RMS value by average value. RMS value can be obtained by multiplying with this. What is form factor? Form factor equal to RMS value by average value. RMS value equal to form factor is multiplied with average value. This is the average value E phase. We multiply. Now the RMS value of EMF is 1.1145 MF T turns per phase. This is the average induced EMF per phase. If the coils were full pitched or concentrated in one slot, the distributed winding pitch factor Kp also we have to consider, because already we derived that it is for distributed windings. The actual available voltage is 4.44 Kp Kd we have to multiply. Kp or Kc, it is Kd distribution factor, coil span factor, pitch factor we have to consider. That is for full pitch winding Kc equal to Kd equal to 1 అవుతాయి కాబట్టి full pitch winding the EMF induced is we can't consider, but practically we are using short pitch windings alternators. This is the EMF equation for synchronous generator and some numerical problems based on EMF equation. 4.44 5 MF T Kp Kd. Kp Kd also we have to consider if it is a distributed winding. Mostly we are using this distributed winding, hence this equation is very important. That is 4.44 Kp Kd pi FFT Ft phase. Now some numerical problems related to that alternator windings we'll discuss in next class. Based on pitch factor, distribution factor, some generated EMF equation 4.44 phi ft phase Kc Kd, like that, based on that formula some numerical problems we'll discuss. It is the problem. Based on that, what are the given data? Number of slots are given 216, 5 conductors per slot. Then Z equal total number of conductors are 216 into 5, because we are given 216 slots each containing 5 conductors. It is running under 250 rpm. The generator alternator is generating 50 Hz frequency. The winding is distributed and full pitch winding. All the conductors of VN page are connected series flux the flux per pole they given that 30 milliweber. The flux per pole is given as 30 milliweber. By reading the problem, after that we have to first note down the given data. After that, Ns equal to 120 F by P. They given that 50 Hz frequency, number of poles are given, P equal to 24 we calculated. Because based on that given data, we can calculate number of poles, P equal to 24. Flux per pole is given as 30 into 10 power minus 3, it is Weber. They given 30 milliweber. Number of slots per pole, N pole pitch we calculated, 216 by 24, 9. Now, N by 3 number of pages, that is number of slots per pole per phase, that is M 9 by 3 gives 3. Slot angle beta is 180 by N. Therefore distribution factor we have to calculate first. Determine the value of induced EMF across each terminal we have to calculate. Distribution factor Kd equal to sin m beta by 2 m sin beta by 2. If you substitute all the values you will get 0.95. It is always less than 1. It is we have to remember, if the distribution factor is more than 1, it is the wrong value. Kc equal to 1 for the given full pitch winding. Full pitch winding coil span factor is equal to 1. Turns per pole, turns per phase we have to calculate T phase, because E phase EMF induced per phase is 4.44 Kc Kd phi F T phase. We are substituting all this. This is the E phase value. Line value, if you want line value you can multiply with root 3 E phase. This is the value. Similarly, another numerical problem briefly we will discuss. A 3-pole, 3-phase, 16-pole star-connected alternator has 144 slots on its armature periphery, each slot containing 10 conductors. It is driven at 375 rpm. The line value of EMF available across the terminals is observed to be 2.657 kV. Find the frequency of induced EMF. Based on this, some problems may be given. According to given data, we written number of poles is, number of slots is 144, conductors per slot is 10. Number of slots are 144. Conductors per slot equal to 10. They given that. Synchronous speed ns equal to 375 rpm. Running at synchronous speed because synchronous generators always runs at synchronous speed. From that, EL also line voltage they given. E line is 2.6.7 kV. It is star connected. EL equal to root 3 E phase, whereas IL equal to I phase in star connected. Given that ns equal to 375 rpm, from that we can calculate frequency f equal to 50 Hz. Number of slots per pole is n equal to 144 by 16, that is 9. Number of slots per pole per phase m equal to already 180 by this n by 3, or you can say 9 by 3 is 3. Slot angle beta equal to 180 by n. 180 by 9 is 20 degrees. Therefore, distribution factor kd equal to sin m beta by t, m sin beta by 2. Distribution factor is sin. If you substitute all the values, you will get kd is less than 1, that is 0.9597. Total conductors equal to slots into conductors per slot. 144 into 10 conductors per slot, it is 1440, that is 1440 conductors are there. Conductors per phase will come, if you divide by 3, 480. Tons per phase means 1 ton means 2 conductors, or if n conductors are there, if you want to calculate tons, we have to divide with 2, that is 480 by 2 gives 240. Now E phase equal to EL by root 3, it is a star connected, we calculate. We know that E phase equal to already one equation, 4.44 EMF equation of alternator, 4.44 kp kd phi f T phase. If you substitute this and you will calculate phi as 30 milliweber, you will get. Similarly, another numerical problem, it is, if you know the formulas of this, we can calculate phi 12 milliweber, we calculated. And the PDF of this notes will be in description or in comments, pinned by that comment. You can download the PDF. Thank you.